Okay, we've got a trig modeling question here to do with a room temperature. It's when I worked this through, it came up with something which looks a little bit implausible. So I was a bit surprised about that, really, because really these questions are very robust. But I realised actually that it's an adaptation of an A level question. So the numbers have been changed, and as such, it's made it a little bit implausible. So I was going to just scrap it and go to the actual original version, but I thought. In fact, it's kind of quite useful to contrast it to the original because it draws out one or two learning points. So here we go. So let's have a look. This first part, express 2 sine x plus 3 cos x in the form r sine x plus alpha. Um, okay, so this part of the question is sort of tends to be known as the R formula, which I don't really like very much. It's a nice snappy title, but it doesn't kind of give an impression of what we're doing, which basically is we're using the two-angle identity in order to express our function um, in this form here, which of course is a shifted horizontally and a stretched vertically sine function. Um, and so that's a kind of extremely important concept in maths. Now, the other thing is, if we ever see an equation like this sort of thing equals some constant, um, then your way of solving it is by doing this transformation into this form, and that's how you would actually solve that sort of equation. Okay, so what do we do? Yeah, we write out this. We normally see this as sine A plus B, don't we? Equals sine A cos B plus um, sine B cos A. So if we write that out and then we compare coefficients of this with this, we're going to get r cos alpha equals 2, r sine alpha equals 3. If we square both and add them, then we're going to get r squared equals 13. And then if we divide the second one by the first, we're going to get tan alpha equals 3 over 2. So alpha is equal to this many radians. Therefore, of course, our original function 2 sine x plus cos 3x is equal to this. Right, the second part, the temperature theta inside a room on a given day is modeled by the equation theta equals 13 plus 2 sine that plus 3 sine that, where t goes between 0 and 24, number of hours after midnight. Using this equation and your answer to part A, deduce the maximum temperature of the room during this day. Well, of course, what we're going to do is we're going to actually use this identity, or basically this identity here, um, where our x is this function in the brackets. So using the identity where that of that where x is equal to that, that's going to give us theta equals 13 plus root 13 sine of this function of t here, which simplified to that. Okay, so in actual fact, we kind of need to complete all that in order to answer part B, but we'll need this later. Now this, we're asked what the maximum is. Well, the maximum of this of any of sine is going to be 1, isn't it? So it varies between -1 and 1, regardless of what's on the inside here. So therefore, the maximum of this function is going to be 13, which is constant, plus root 13 times 1. Okay, 13 plus root 13. And the minimum of the function will, of course, therefore will be 13 minus root 13, minus root 13, which is 13 plus root 13 times -1. Okay, and just a couple of things to notice about this curve here is that this constant here basically determines what is a full cycle of this sine wave. What is that length there? And so that's going to give us that the full cycle is 12 hours. 12 hours, because if we substitute t equals 12 in here, we're going to get, well, if we substitute t equals 0 in here, we're going to get 0 for this. And sine 0, 0. And then substitute 12, pi by 6 times 12 is 2 pi. So that's when the sine function has done a full cycle. Okay, so a little check there that you can just check what's the full cycle is. Well, 12 hours is a bit of a strange thing in this question, isn't it? The maximum temperature of the room during this day is what we're asked for, and we've got a 12-hour cycle. So that immediately makes you think, well, actually, we're going to get two solutions out of this. Okay, I mean, the other thing is all that checking there about the cycle time. This bit doesn't matter, but this is important in the context of the whole question. Um, it's sort of saying we're not going to get our minimum or our maximum at midnight, are we? Right, okay, so that's a little bit about that. Then C, find the time of day when the maximum temperature occurs, giving your answer to the nearest minute. Okay, well, we know what the maximum is, and we know that the maximum is going to occur when this is equal to 1. So basically, that's what we're going to solve, is that equation. And that's going to give us that the argument of this function is equal to is going to be equal to the arc sine of 1. We'll take pi by 2 as being the primary solution, and therefore t is equal to that. That's just rearranging, and therefore t equals this, and t equals 4:57 a.m. Right, okay, that's a little bit implausible anyway, isn't it? Kind of rooms tend to rise up in temperature through the day. We'd normally sort of think there would be just one maximum temperature, probably early afternoon sometime. But on this one, yeah, we got 4:57 a.m. Of course, the other thing with this is it's a 12-hour cycle, so we're actually in a 24-hour period. We're going to get another maximum, which will happen 12 hours later at 4:57 p.m. Right, okay, so those are our answers to this particular problem. But normally, as I say, these problems tend to be fairly robust in how plausible and how true they are to real life. Um, this, incidentally, is courtesy of Desmos, is what we're talking about. I mean, I put the function here in its two forms. This is the raw form, this first one given by the question, and this is the transform one. And there's only one graph here, and that's because these two sit on top of each other. So that sort of demonstrates that this really is a kind of a reform of this first function. And we can see from here that the full cycle is indeed 12 hours there. Here we've got our maximum. Here, just at the sort of time of the answer. And then we've got another one down here, which is within our 1 day, but later on in the afternoon. Right, okay. So, and this is the original question from 2020 paper 1. So you can see the numbers have been changed, haven't we? We've got different coefficients for sine and cosine, which would give us r, and this would give us r of root 5. Okay. And then so yeah, so the minimum would be that should be root 5 there. So that would be 5 the minimum will be the maximum will be 5 plus root 5. Um, and we'll just change that. 5 plus root 5, and the minimum will be 5 minus root 5. Okay. Um, but sort of perhaps more significantly is what's happening here with this function. So we've got our coefficient of t is pi by 12. Okay, so that sort of doubles the cycle time. So that's going to give us um, uh, that a full cycle is 24 hours. This 3 rather than the 2 also means that we're effectively shifting further. So our maximum time is being shifted further to the right. And actually, therefore, it kind of comes into more plausible territory, which is around about sort of nearly 2 o'clock in the afternoon, I think. Right, so that basically is the original question, and so hopefully that's kind of helps to illustrate some of the features of these problems by contrasting those two versions of the same thing. A little bit of a warning to people adapting questions is to uh, make sure you do it right. Okay, so basically that's it. Hope it's been useful, and thanks for watching.